Hello, can you hear me? We have a technical problem. So don't stay away because here you can see me, I can see you. Is better. Oh no. I'm happy to explain to you later, but I think he got it already, so he can explain to you. Hello, the people in Zoom. Can you hear me now? Sorry, just now I was muted, but you didn't miss anything because we have a technical problem in here. So there's an issue. Right, so thank you very much for your kind patience. We are only 5 minutes late, so that's okay. Thank you very much. Now let's start. Let us recap what we talked about last time. And then today's lecture, the reading is section 3.2. You must read it, okay? And because there are all the examples there, all the examples are there and you need to look at them, all right? Last time, we covered the topic of section 3.1, which is the probability density function. I don't know whether it's 3.2 or 3.3 is one of them, okay? So we said that, okay, we introduced the notion of a continuous random variable, which has a probability density function f of x. Now, what are some of the properties that the probability density function has to satisfy? Number one, it must be non-negative for all x on the real line. So you cannot have a probability density function that is negative. And number two, it must integrate to 1. All right, so f of x u du must be equal to 1 from infinity to infinity. And it has the property of the following. If I'll make this as 3. If I have a small number delta, then what happens is that the evaluation of the probability that x is between little x and x plus delta, that is the integral from x plus delta to x of f of x u du, that is equal or approximately equal to delta fx of x. Okay, so that is one property of the probability density function. And in fact, what I have already mentioned is that if I have a subset, if B is a subset of the real line, then I'm interested to evaluate the probability that x belongs to B, then I will simply integrate over the region B. Okay, so I think I always use U here, but it doesn't matter what you use as long as you know what is happening. Okay, so for example, if B is the interval AB, okay, so that is the closed interval AB, we are asking the probability that x belongs to the interval AB. Now that can be written as the probability that x belongs to x is A all the way to B inclusive. Now that can be written as the integral of A to B of fx of u du. Okay, and we mentioned last time that it doesn't matter whether we use the strict inequality here or the non-strict inequality here. Doesn't matter too much. Okay, so that was what we mentioned last time. And we mentioned a few statistics that we have to know how to compute, namely the expectation and variance. So these are given by some standard formulas. So the expectation value of x is equal to the integral from minus infinity to infinity u fx of u du. I think the book uses t as the argument, but doesn't really matter. Now, if you're interested to evaluate the expectation of something else, some function of x, then you just have to replace the u in the previous formula by g of u. Okay, and you integrate in the usual way. Okay. But there are some functions that are more important than others. For example, those that lead to the variance. So if we take g of x or g of u to be u minus expectation value of x, this is a special function. So you take away the mean and you square the resulting number, so that is a particular function. If you take the expectation value of this function when I put in the random variable x, then you get u minus expectation value of x squared dfx of u du. This has a name, and this is called the variance of x. Okay, and actually, just like the discrete case, the variance of x can be written in a couple of different ways. It can be written as expectation of x minus expectation value of x quantity squared. And it can also be written as expectation, the second moment, this is called a second moment, minus the first moment quantity squared. So I think all of you know this, so I will not belabor the point here. Now, there are some functions that are more important than others. For example, the linear function. So if in particular, I create a new random variable z that is ax plus by plus c, then it is always true that expectation value of z is equal to a times expectation value of x plus b times expectation value of y plus c. All right, where a, b, and c are scalars, are just real numbers. X and y are arbitrary random variables. Arbitrary random variables. Okay. Now, if in addition x and y are independent, then we can say more independent. Then we can say something about the variance of z. And in particular, the variance of z is a squared variance of x plus b squared variance of y. Note that this formula holds when x and y are independent. When x and y are not independent, then there are some extra terms here that we will talk about later on. So these are some standard things that we already should know, and I don't want to belabor the point because I have already talked about last time. So just in summary, you should know what the PDF is. That the PDF is something that is non-negative and it integrates to 1. So for example, if I have a particular random variable, its PDF looks like this. You know, it looks like this, say. Okay. And then if I'm interested, for example, to evaluate the probability that x takes on the value between a and b, then I will try to evaluate, okay, the area under this graph here. Okay, so that represents the probability that x belongs to the interval AB. Okay, so we basically have to integrate this. Then it's a matter of whether you know how to integrate things, right? Okay, so sorry to the people in the lecture theater, I just blocking you. Right, okay, right. So this is where we left off last time. And today we want to introduce a new concept that somehow is very useful. And we will see it in many examples later on, okay? It is super useful because it actually unifies both discrete and continuous random variables. And this quantity is known as the cumulative distribution function, and in short, the CDF. So this is in contrast to the PDF, which is something different, okay? Now, this concept here allows us to very neatly unify both discrete and continuous random variables. Because this object exists for all discrete and continuous random variables, for any random variable, this object exists. Now, when we talk about discrete random variables, we talk about probability mass function. When we talk about continuous random variables, we talk about PDF, probability density function. So now, these are different objects, right? For discrete random variables, the probability density function does not exist, right? For continuous random variables, it makes no sense to talk about the probability mass function. But for any random variable, it makes sense to talk about the cumulative distribution function. Okay, so what is it? The cumulative distribution function of any random variable x, be it discrete or continuous or neither. All right, they are random variables that are neither discrete or continuous. Okay, is the function which is denoted by capital F, capital X, little x. So these things here are uppercase and this is lowercase. It is really important to write this properly. And what is this function here? This function is nothing but the probability that x is less than equal to x. And here it makes a big difference that this is less than equal. Okay, don't put less than. This is the definition. All right, now in the special case that x is the discrete random variable, how do we write this out as the PMF? All right, so I'm going to write this as k equals to minus infinity all the way up to x of the PMF. So this basically accumulates all the probability masses from minus infinity all the way up to x, including x. All right, for the continuous case, we integrate all the way up from negative infinity up to x of fx of u du, x continuous. All right, so intuitively what's happening is that the CDF accumulates all the probability masses up to and including x. And including x. So the including is important. Right, this is actually a bit abstract. So let me give you some simple examples. Okay, simple examples. So just before we give simple examples, this is actually the PMF of the discrete random variable x. And this object here is the PDF of the continuous random variable x. Okay, so this single object, the cumulative distribution function, unifies the whole world. Because now we don't need to talk about discrete or continuous random variables. They are all characterized by this single function of a real number x. Okay? This thing is a very meta object because no matter whether the random variable is discrete or continuous, this thing exists and we can work with it. So for example, okay, this example is not in the book. I make it up, but it's even simpler than those in the book. The PMF of x. Say we have a coin, all right? We have a coin that looks like this. The PMF is like this. All right, so there's a PX of K. And whenever the coin is tails, the probability of it being tails is 0.3, okay? And that's represented by 0. Now, the coin is heads with probability 0.7, okay? Sorry, this is not in the book, but it's similar to the examples in the book. It is simpler. So what is the corresponding cumulative distribution function or CDF? All right, now let's look at this. We can plot that, all right? So the cumulative distribution function fx of x here. Now, the formula for the discrete case is this. So I'm going to sweep the x from the negative infinity all the way up to positive infinity. All right, sweep it, all right? So now I go here. Is there any mass here? No. There's no mass on the left-hand side. So my cumulative distribution function will be very boring on the left-hand side. Nothing happening here. Okay, sorry, I have to use a different color. Okay, it's very boring. There's nothing happening up here. Okay. Nothing happening. Now, once I reach 0, what happens? I have to accumulate the mass at 0, and the mass at 0 is 0.3. So at the point 0, the cumulative distribution function is 0.3. Okay, so it's here. Right. So we can do a simple sanity check. Okay, what is the cumulative distribution function at 0? It's the probability that x is less than equal to 0. Now, that is the probability exactly that x is equal to 0, because the probability that x is less than 0 is exactly 0. And this is equal to 0.3. Understand? Now, so this value is 0.3. Okay, now you move along, you trudge along, you go to 0.5, x is 0.5. Did you pick up any more probability mass? No. You walk here, walk here. Did you pick up any probability mass? No. You continue walking until you walk until 1. Then did you pick up any mass? Okay, until 1, oh, there's a jump. You pick up some money. You pick up 0.7 mass. And then you're already here, right? So this is like this, okay? You walk until 1, then you pick up 0.7 to you have already got 0.3. So you pick up more, and then you reach 1. Okay? So this value here is 1, and this stays flat. This distance here is 0.7. Now, I may not draw this to scale, but I hope you get the idea. So you walk from the left-hand side all the way until the right-hand side, and you continually pick up probability masses. The book has a much more complicated example, which you should read. It's too difficult for me to draw the example. Right, David? Yeah, same idea, right? I'm not going to draw complicated things. My artistic skills are not so good. But I hope you understand this. So this is a discrete example, okay? So now let's move on to a continuous example. Okay. Any questions here? Now, the meticulous student in you would notice that I'm very meticulous also. Why? Because at 1, okay, say at all these jumping points. Yes, Wei Xiao, right? You write. Yes, you write this. Let me flash this to the whole lecture theater. Yes. So Cheng Wei Xiao asked a question. What is fx? But Cheng Wei Xiao, you have to write capital F. All right. You cannot write small f. That is wrong because that represents a probability density function. Fx of 1. What is the meaning? It's the probability that x is less than equal to 1. That is the probability that x is equal to 0 plus the probability that x is equal to 1, which is 0.3 plus 0.7, which is 1. Understand? So Cheng Wei Xiao, you must write f sub x of 1 is equal to 1 this way, nothing else. Okay? Right. Everyone understand? Okay, what I want to say is that at this point 1, it takes on the higher value. All right, it is not the lower values. Hence, we put the empty circle here and we put the colored circle there. Understand? Everyone got it? This is super important, right? This is the essence of today's lecture. All right, I know some people here. Very good. Okay, so I can move on. Okay. So now let me talk about the continuous example. PDF of a uniform random variable x on AB. Okay. So now we have a PDF that is like this. Fx of u. This is A, that is B, and we have this box here. Maybe I should use this red for the box that I want to draw. This value here, hopefully you appreciate that this 1 over B minus A. Okay, this is in order for the area here to be unity. So now we want to be able to draw the CDF. Okay, we want to eyeball and draw the CDF. We don't actually need to do too much work. How do we draw this? It is capital F of x. So you know, Cheng Wei Xiao, you must put capital F. Otherwise, it is confused with the little f, which is the PDF. Okay. So now, again, we go to the left-hand side. All right. We see whether we pick up any probability mass here. No, do we? No, we have no probability mass here. We are not picking up any money until we reach A. Now, when we reach A and we trudge along, we move along, then we continue to pick up probability mass because we are going to pick up mass like that, right? And so what happens here is that you have these 2 critical points, A and B here. And then you are basically going to, what's happening here? When x is between A and B, Now the fx of x is the integral from a to x of fx of u du. That is a formula for the CDF, if you recall from the formula here. Okay. But we are only starting at a because there's no action before a. No action at all. So now this is integral from a to x of 1 over b minus a du. This yields x minus a over b minus a. So it's a linear function. Now the pedantic people among you, we call this a affine function. All right. So it's an affine function like this. All right. And goes all the way up here. All right. So at this particular point, B, at a point B, what do we have? So let's ask Cheng Wei Xiao. You see, fx at B is equal to, if I plug into this formula, B minus A over B minus A, which is unity. Okay. So at this particular point, this is 1. This is 0. 0. So the point I want to try to make is the following. All right. Let me get rid of all this. So suppose I'm interested in x here. X is some number between A or B, between A and B. And I'm interested in this particular area here. Okay, that represents what? This business here represents the probability that x is between, the probability that x is between A and little x. Okay, now on the right hand side, we have this x here. This point here represents, again, nothing but the probability, okay, the probability of A to of x between A to x. But the probability that x is less than A is 0, okay, because there's no mass over here. So in fact, this is the same as the probability that x is less than or equal to x. Okay, this point exactly. Okay, so this is the same as probability that x is less than or equal to x, because there's no mass on the left hand side. So does everyone understand this picture? It is of crucial importance to understand this. Oliver? No. Okay, never mind. I'm happy to re-explain this thing. Okay. So now what we have here is that here, this is the probability density function of a uniform random variable. Okay. So it has this shape here. Now I want to be able to figure out what is the cumulative distribution function. Okay. So basically the formula says I should integrate from the left up to a point that I'm interested in. So I'm integrating from A all the way up to X of the PDF here. The PDF takes the form 1 over B minus A here. Okay. Now if you integrate this, because this does not depend on you, so it can be brought outside. And so we are left with the range of integration here. If you want to do this slowly, you can do this slowly. All right. But you get to this point. So this is a linear function. So this grows linearly like that. Up to this point where this does not apply anymore, this saturates at 1. Yes, because probabilities cannot be more than 1. Probabilities cannot be more than 1, so this must saturate at 1. Everyone understand? Very good. I don't know anyone else here. Otherwise, I will call names. All right. So the point is that for continuous random variables, okay, for continuous random variables, I don't know whether you learned this before or not, but there's this thing called a fundamental theorem of calculus before this class. So I just want to mention briefly that for continuous random variables, we can recover the PDF from the cumulative distribution function by differentiating. Now, we get the CDF from the PDF by integrating. So if we have the CDF and want to get back to the PDF, we differentiate. Okay, I'll write this out properly. In particular, this is the PDF, and we can get it from the CDF by differentiation. So this is one thing that we can recover, we can easily get. I'll write this again later on. This is just a side remark. Okay. Now, I want to mention some very important properties of the CDF. Some very important properties that you should internalize of the CDF, of any CDF. Now, the CDF is defined as f of x. This is probability that x is less than equal to x. Okay, number one, fx, the CDF, is monotonically non-decreasing. No, folks. Math people would say non-decreasing, like me. All right. Common people would say increasing. You know what's the difference between non-decreasing and increasing? Increasing means if you take 2 points, x and y is bigger than x, then f of y is bigger than f of x. Okay. Non-decreasing means you are not decreasing. Okay. So for example, you could have this. This is a valid CDF. At this point here, is it increasing? No. David is correct. It is non-decreasing. It cannot decrease. So you cannot have a CDF that do like this. Okay? Cannot. Non-decreasing is the right word. And you can see even for continuous random variables like this, here you are strictly increasing. Good for you. Good. Strictly increasing is non-decreasing. Okay? But here you're flat. Flat is not increasing. So it is non-decreasing. Understand? So mathematically, what is the meaning of non-decreasing? For all x prime such that x is less than equal to x prime, we have that f of x is less than or equal to f of x prime. Okay, so that is the meaning of non-decreasing, cannot decrease. Right? Understand? Can be increasing and can be constant. Perfect. Okay. So another property is the following. As x goes off to minus infinity, the cumulative distribution function goes off to 0. Okay, so you look at all these pictures here. This is the cumulative distribution function. As I go off to minus infinity, I have 0 probability mass. Okay, here I have very little probability mass. And in particular, if I go all the way, I shoot all the way to the left-hand side, I pick up nothing. And so I have probability 0. Okay. So here the reason is that f of x is probability that x is less than equal to x. And if I take x going off to minus infinity, that is equal to 0. That's the reason. Okay. Because x, the random variable x is a real valid random variable, it cannot take on the value minus infinity. It must take on some real numbers. So if I push the little x all the way to minus infinity, I pick up no probability mass. Understand? Now, conversely, if I take x to go off to plus infinity, all right, then what do you think fx goes towards? 1. Perfect. Thank you very much. So as I make x goes off to plus infinity here, all right, plus infinity here, then what happens here is that I pick up everybody. I pick up all the probability masses I can pick up, right? So if I make this, if I take x to go off to plus infinity here, I pick up everything, all the things on the left-hand side. So I have to have probability equal to 1. Understand? Right. So these are some corner cases that we need to worry about. All right. So here are some qualitative comments. If x is discrete, is a discrete random variable, then f of x is piecewise constant. Right? So for example, here we have a discrete random variable with PMF. Then it turns out that, oh, we have this step function here. It's multiple steps, okay? Now, if you have more probability masses here, just like in the book, I don't want to draw this, then here you have going to be more steps. There are going to be more steps. But these steps can only go up, cannot go down, because the CDF is non-decreasing. Okay. Now, furthermore, if x is continuous, then we have some other property. Okay. If x is continuous, then f of x is continuous in X. Now, you may wonder what is continuous mathematically. Actually, the notion of continuous requires 1 semester to learn in MA 2108, which I sometimes teach. Right? You need 1 semester to know what is the meaning of continuous. But I can tell you what is continuous in 1 sentence. A continuous function is one in which you can draw without lifting your pen off the paper. That is the meaning of continuous. You can formulate this in a proper mathematical way as well, but that's the meaning of continuous. Okay? So you don't need to worry about that because that is 1 whole class. So you don't need to worry what's continuous. Okay. And in particular, if X, so we want to recover the CDF from the PMF and so on and so forth. If X is discrete and takes on only integer values, then the PMF and CDF can be obtained from each other by differencing. Obtained from each other by summing and differencing. So specifically, we have that the CDF f of xk is a sum all the way up to k from minus infinity p of xi. So this is nothing but the probability that x is less than equal to k. I'm looking at all the probability masses that can only sit on integers, and I'm summing them up. So the picture is as follows, okay? I'm interested in the probability that x is equal to k. So I have this -2, -1, 0, 1, 2, k. All right, and I have some probability masses here. So on and so forth here. So basically what this means is, and what this means is that I'm summing up all the probability masses from minus infinity all the way up to and including k. Okay, so that gives me the CDF. Now, how do I recover the PMF from the CDF? Look at this, P of x, k, that is equal to the probability that x is exactly equal to k. But I can get this as the probability that x is less than equal to k minus the probability x is less than equal to k minus 1. Right, the probability that x is equal to k is everything up to and including k minus everything up to and including k minus 1. So here I excluding k. Here I including k. All right. So this is nothing but fx evaluated at k minus fx evaluated at k minus 1. So this is called differencing. Taking the difference. Differencing. This is called summing. Okay, so summing and differencing are duals of each other in some sense. Okay. So the last property, or the second last property, the penultimate property, is that is the following. I've already mentioned this. If x is continuous random variable, then the probability density function and cumulative distribution function are related to each other by integration and differentiation. So these are operations that are dual to each other in some sense. Okay, this is through the fundamental theorem of calculus, which you may or may not know. F of x is equal to, I have already written out this formula, fx of u du. How do you recover this guy from this guy? Now this theorem here is very major. This is one whole class actually. All right, you differentiate this. All right, you differentiate this to recover the integrand. Right, so f of x is d by dx of fx of x. Right, so this is called integration. Operation. This is called differentiation, and these two are dual to each other. Differentiation. Okay, so we'll see numerous examples of this. This is a bit abstract, I know. Okay, so this is some property. Okay, these are some properties of the cumulative distribution function that are in the book. I want to mention one more property that is not in the book. I make this up, but it's true. Any cumulative distribution function fx is right continuous. Now, if you do not know what is continuous, of course, you do not know what is right continuous. But you see look at the pictures here. All right. If you come from the right-hand side, if you are walking from the right-hand side, you will hit this point here that is included. If you go from the left-hand side, you will hit this point that is not included. All right. So this is not left continuous, but it's certainly right continuous. So what we mean is the following. All right. F for every x, right? Fx of x is equal to limit as delta goes towards 0 from the right-hand side, fx of x plus delta. All right. Now, this is not so important. It's not in the book. You can absorb it or not absorb it. But what it's saying is that if I come to x from the right-hand side, I recover the value of x at the limit. Okay. So there are some exercises that we will do that require this, but this is not so crucial if you don't fully understand the notion of right continuity. So to end off this lecture, this short lecture, which I like, okay, I want to do one example that shows you the utility and the power of the cumulative distribution function. I don't think we have time to do 2 examples, so I'll just do 1. All right. So your professor is very nice. He allows you to take 3 exams, 3 independent exams, and your exam score is the maximum among the 3. Okay, so xi is your exam score taken on day I, and I is in 1, 2, 3. If you're not happy, you take it again. Okay, and in fact, xi is uniform. It's a discrete uniform random variable on the set 1, 2, all the way up to 10. Okay, so its PMF looks like this. PMF looks like this. Okay, 1, 2, all the way up to 10. That is TXI. Okay, so it's uniform. And I think most of you should be able to tell me that this height is 1 over 10 because all the stems should add up to 1. Agree? So that is, so every time you take the exam, you're going to get a random number from 1 to 10, inclusive. All right. So we want to figure out, okay, it's fairly easy to write down the PMF of each exam score that you're going to get. All right. It's basically this, 0 otherwise. Okay. Now, we will see that the cumulative distribution function is very important and useful. So the professor allows you to report x, which is the maximum of the exam score over 3 days, x1, x2, x3. That is your exam score. You can have 3 tries. Okay. So what is the probability mass function of your eventual exam score, which is this x here, x defined as this. So that's very nice. You have 3 tries. Okay, we did something like that in the tutorial. I don't know whether the other tutor went through this or not. Maybe he did. Okay, so fx. So we want, okay, what do we want? We want the PMF of x. All right. So those people in my tutorial class would know that when we want the PMF of something, the first question we have to ask is, some people answered it correctly, and you also partially answered it correctly. We have to figure out the support of x. Now, whenever I try the exam, I get the number 1 to 10. I may be super unlucky, and every time I got 1. The maximum is still 1. All right. So what we want the PMF of x, its support is still 1, 2, all the way to 10. Oliver, that's the answer I'm looking for. I want the support. The support, which is a set of values that x can take on. If I have three numbers, each one of the three numbers can take on the value 1 to 10, then the maximum can also take on the value 1 to 10, right? Yeah, logic, right? Okay, so now we want the PMF of X. Its support is this. So we have to figure out what is the PMF. So the way to do this is we do this via the cumulative distribution function of X. And then we'll see that we can get the PMF via differencing, because we are in the land of discrete random variables. Okay, so let us figure this out. The PMF of X, which is the maximum of X1, X2, X3, evaluate at some K, fix K to be in 1, 2, all the way up to 10. So that is a fixed integer. There is a probability that X is less than or equal to K. That's the definition. Okay, so the definition of my eventual exam score is the maximum of my 3 tries, maximum of X1, X2, X3 less than or equal to K. That's the meaning. Okay, that's just the meaning. Now, if the maximum of 3 numbers is less than a certain number, all 3 must be less than a number, right? Right. So if the height of Sonia, David, and Oliver is less than, say, 1.85, then everyone has to be less than 1.85. That is logic, right? So this means that the probability that Sonia's height is less than K, David's height is less than K, Oliver's height is less than K, all this must hold simultaneously, right? Now, at this point in time, you cannot do anything if I don't give you further information. Every day, your exam score is independent. If it is independent, so let's say the xi's are independent. Otherwise, this cannot be done. All right. Say you didn't revise across the days and the tests are all independent. All right. So this becomes the product. Probability x1 less than k, probability x2 less than k, probability x3 less than or equal k. This is being used here. Okay. That's the meaning of independence. But each one of the random variables xi is uniform on this PMF. So suppose k is here. All right, suppose this k is here. Then what is the probability that xi is less than or equal to k? It is nothing but k divided by 10. So for example, if k is equal to 2 here, what is the probability that xi is less than or equal to 2? You are picking up these 2 stems, right? So it's 2 out of 10, right? Generally, it is k out of 10. So you have this k over 10 times k over 10 times k over 10, and we can write this as k over 10 cubed, right? Understand? That is the probability mass function for each person, each test that we take. Then each test that we take uniform random variable on this support set 1 to 10. So if k is equal to say 7, there was a probability that xi is less than 7. It's 7 over 10, right? Less than or equal to. We must say equal to. Okay. Understand? So it's k over 10 in general, and then there are 3 of them, so we have to take cube. Okay. Now, if we want the PMF, we can get it from the CDF by differencing. What is the meaning of differencing? Remember that Px of k is equal to nothing but Fx of k minus Fx of k minus 1. And here k runs from 1 to all the way up to 10. All right, this formula I mentioned just now when I mentioned the properties of the PMF and the CDF. If x is discrete and takes on only integer values, then these 2 objects can be obtained from each other by summing and differentiating. If you want to get the CDF from the PMF, you do the summing. If you want to get the PMF from the CDF, you do differencing. Okay? So we have exactly satisfied the conditions of this result because our random variable takes on values on the integers and it's a discrete random variable. So we can get the PMF by differencing by this formula exactly. So all that remains is to plug the numbers into this. Okay, so we have k over 10 cubed. Let me write this properly. K over 10 cubed minus k minus 1 over 10 cubed. And this holds for k running from 1 to 10. Okay, that's the support. Okay, understood? Right, so let me repeat this. This is a new concept. Okay, so you are going to take your exam on 3 different days, and your perform. Okay, I'm going to explain to Alvinci later on. Okay, I can draw a picture later on. Very good question. Where am I? Let me repeat the steps. All right. The step is that, okay, you are allowed to take the exam 3 times and on 3 independent trials. The first trial is called X1, the second trial is called X2, the third trial is called X3, and each of the trials uniform on this discrete random variable, which is uniform on 1 to 10. Okay. Now, we want the PMF of X, and its support is this, right? So we write down the CDF, but X is defined to be the maximum. Okay. If the maximum is less than or equal to K, all these guys have to be less than or equal to K. Now, because all of them are assumed to be independent, we are split it up like this. And then each one of these guys is identically distributed. And in particular, the probability that Xi is less than or equal to K is K over 10. So it is K over 10 cubed. Recall that if you want a PMF, we can get it from the CDF by differencing. This is the differencing formula. And so we can plug the numbers in as follows. Okay, so that's the way we do it. Now, to end it off, I want to answer Alvinci's question. What is the purpose of this? All right. Now, recall that at the very beginning, our performance, if your professor only lets you try once, is this performance. Okay. If your professor only lets you try once, then your grade is uniform from, your mark is uniform from 1 to 10. Now, this guy here is a bit difficult to draw out if you do not have intuition, but I have intuition, so I'm going to draw it for you. So you see, you can actually improve, okay? If you did 3 tries, intuitively, your maximum score is going to be better than 5.5. So here, the expectation of Xi, just by inspection, is 5.5, right? It's the average between 1 and 10, 11 over 2. All right. So here is the PMF of X, and X is equal to max of X1, X2, X3. Okay. So what we have here is 9 over 10. Okay. So what is going to happen here is the following. I do the calculation in my head. 1, 2, 3, 4, 7, 8, 9. Since Alvinci asked me this question. Okay. The whole PMF is going to be skewed to the right-hand side. And in particular, say at 10, what is the chance that you get perfect score? Initially, it was 10%. Initially, it was 10% here. Now, if you put the number 10 inside here, you get 200. You get 28.1%. I did it in my head. Instead of 10%, you get 28.1%. 7.1. Yeah, 27.1%. Instead of 10%. So you get skewed. Right? So instead of 10%, you get full marks. 27% of the time you get full marks. Pretty decent, right? Not bad, right? I can do this in my head. Basically, I plugged the number 10 inside here. And during my time, we have to do mental sums. So I did this mental sum. I put 10 here. All right, now I put 9 inside here. 9 is a bit difficult. So 729 minus. Okay, so I don't know. You put me on the spot, but it's going to be like this. It's going to be skewed to the right hand side. My drawing here is not very good, but you get the idea. Your performance is going to be skewed to the right. So by giving you this chance, right? By giving you the chance of trying 3 times, your performance is skewed to the right-hand side. And the chance that you get full marks is 27% instead of 10%. All right, and we did this calculation through the CDF. All right. Understand? So, Alvin Chi, does this answer your question? Oh, really helpful. Thank you very much. Okay, you see here, Alvin Chi. What is the chance if you only take the exam 1 time, you get 1 mark? It's 10%, very high. Now, if you take the exam 3 times, what's the chance that you get only 1 mark? That means you must have gotten 1 mark for each trial. This is, instead of 10%, it is only 0.1%. Significantly reduced. Okay, for this point here, only 0.1%. Okay, so the chance that you do abysmally is only 0.1%. The chance that you do very well is 27.1%. Pretty good. Are you typing your calculator to see whether I'm correct? Yeah, I'm sure correct. Right. So so your chance, your performance gets skewed to the right-hand side. All right. Okay, so this is where I will end. This is where I will end today. And I'll see you again on Thursday. I hope to see Oliver here. I want to see you. And I want to see more people from the Zoom come here to entertain me. All right. Thank you very much. Alvin Chi, understand? Thank you. Bye-bye.